Welcome. Let the evenings settle around you now, and let your body sink a little heavier into whatever is holding you. There is nothing you need to do here but rest. Tonight, we drift outward through the spiral galaxies, starting from the place where you already are, a small blue world tucked inside the turning arm of a much larger galaxy. Let your breathing slow, and let the sky begin. The sun rests inside a spiral arm of the Milky Way galaxy. It sits along a broad ribbon of stars and gas, one of several such ribbons winding through the disk. We are not at the center and not at the far edge, but somewhere comfortably along one curving lane among many. Every star you have ever seen from Earth shares this same neighborhood. It is, in a quiet sense, home. The Milky Way's disk stretches roughly 100,000 light-years across. That is far enough that light itself needs 100,000 years to cross it. The disk holds hundreds of billions of stars, arranged in wide sweeping arms around a dense center. From end to end, it dwarfs any distance the mind is used to measuring, and still, it is only one galaxy among countless others. Earth orbits the galactic center once every 220 million years. This single loop is sometimes called a galactic year. The last time our solar system passed this point along its orbit, dinosaurs had not yet appeared. We are moving, always, though the motion is too vast and too slow for any of us to feel. The Milky Way has between 2 and 4 major spiral arms, and their exact count is still debated. From within the disk, astronomers cannot simply step back and count them by eye. Different surveys, using different wavelengths of light, trace slightly different patterns. Some maps show 2 dominant arms, others suggest 4. The true shape remains a patient, ongoing puzzle. Our galaxy's central bulge holds an ancient population of stars. Packed closely together near the core, these stars formed long before most of the disk around them existed. Their light is often redder, their orbits older, their stories longer. They circle the center in a dense, glowing swarm, largely undisturbed by the younger stars further out. A bar of stars runs through the Milky Way's core, giving it a barred spiral shape. This bar stretches across the central region like a straight beam laid through the bulge. Spiral arms unwind from its 2 ends, curving outward into the wider disk. Roughly 2/3 of spiral galaxies share this same barred structure at their heart. William Herschel mapped the sky by star counts and glimpsed a flattened shape to the heavens. Working through long nights in the late 1700s, he counted stars in patch after patch of sky. From those careful tallies, he sensed that the stars were not scattered evenly in every direction. He had, without quite naming it, brushed against the outline of a disk-shaped galaxy. The spiral arm we live in is called the Orion arm. Though it is more a spur than a major arm, it bridges 2 larger arms nearby, a modest connecting strand rather than a grand structure of its own. Even so, it carries our sun, our planets, and every star we can name by sight. Grand or not, it has been enough to hold a home. Mapping the Milky Way from the inside resembles drawing a floor plan without ever leaving one room. Astronomers must infer the shape of arms. They can never step outside to view directly. They rely on the motions of gas, the positions of stars, and light that slips through dust in narrow windows. Slowly, patch by patch, a picture of the whole house comes together. The galactic center lies hidden behind thick dust, invisible to ordinary eyes. Clouds of gas and grains block most visible light from reaching us across that distance. What glows brightly in radio and infrared images remains dark and silent in an ordinary photograph. The heart of our galaxy keeps itself quietly out of sight. At the center of the Milky Way rests a supermassive black hole, unseen but deeply felt. Its gravity does not pull stars in so much as hold their orbits together, the way a hand might rest lightly on a spinning top. Stars near it race around at astonishing speed, yet stay bound. Nothing crosses that gulf and returns. Its presence anchors the galaxy's slow, patient rotation. Vera Rubin spent long nights in the 1970s measuring how fast stars moved at the outer edge of spiral galaxies. She expected them to slow down, following the pattern of visible matter thinning toward the rim. Instead, the outer stars kept pace with the inner ones. The result unsettled her, though she trusted the instruments. It would take years before the wider field caught up to what she had found. Stars near the Milky Way's rim move faster than the visible stars and gas can explain. If gravity came only from what telescopes could see, those outer stars should drift outward or lag behind. They do neither. Something unseen appears to be holding them in place, contributing far more gravity than glowing matter alone provides. The outer disk behaves as though it weighs more than it looks. Dark matter seems to form a vast, invisible halo wrapped around every spiral galaxy's shining disk. It gives off no light of its own, betraying itself only through gravity's quiet influence on stars and gas. Cosmologists still debate its exact nature, though the evidence for its presence is widespread and consistent. Picture a great, unlit sphere cradling the bright disk we can actually see. The visible galaxy may be only the smallest, brightest part of something far larger. Spiral arms are not fixed rivers of stars flowing endlessly around a galaxy. They are lanes of density, places where stars and gas happen to be crowded closer together for a while. A star does not stay locked inside one arm forever. It passes through, much as a traveler passes through a busy stretch of road before continuing on a quieter path beyond it. Stars drift into spiral arms and drift back out again, much like cars easing into a traffic jam and then pulling free of it. The arm itself stays roughly in place, a pattern moving through the disk at its own pace. Individual stars slow down as they enter, linger briefly among the crowd, then speed up again as they leave. The jam persists long after any single car has passed through it. Inside the crowded lanes of a spiral arm, gas compresses under gravity until new stars begin to form. Clouds of hydrogen thicken as they pass through the arm's higher density, collapsing here and there into glowing knots. Some of those knots ignite into stars within a few million years. The arm, crowded and busy, becomes a kind of nursery drifting slowly through the galaxy's disk. Young blue stars burn brightly and briefly, and so they trace the spiral arms where they were born. They live only a few million years, far too short, a span to drift very far from their birthplace before dying out. Their light marks the arm's shape clearly, glowing hot and blue against the darker spaces between. By the time they would have wandered away, they are already gone. Older, redder stars live for billions of years, long enough to wander far from wherever they began. Over time, they spread more evenly across a spiral galaxy's disk, no longer confined to any single arm. Their light glows warm and steady, rather than sharp and blue. Look closely at a galaxy's disk, and the older stars form a softer, more uniform haze beneath the brighter, younger pattern. Far above and below the Milky Way's disk, looping streams of stars trace the paths of smaller galaxies torn apart long ago. Gravity pulled at their loose edges first, then unraveled them entirely, scattering their stars into long, curving trails through the halo. Those trails still hold together loosely, faint evidence of galaxies that no longer exist as separate things. Their stars now belong quietly to the Milky Way's outer reaches. Feel the weight settle into your shoulders first, heavy against the mattress. Let that heaviness spread slowly down through your arms, into your hands, until your fingers stop trying to hold anything at all. Your hips sink next, then your legs, one after the other, growing dense and still. Even your eyelids feel the pull now. Let them close. There is nowhere lighter to be than exactly where you are. Globular clusters circle the Milky Way in a vast spherical swarm, drifting far above and below the flattened disk. Each cluster holds hundreds of thousands of stars, packed closely and bound tightly by their own gravity. Unlike the disk's orderly spiral lanes, these clusters loop through space on tilted, wandering paths. Some of them are older than the disk itself. They orbit quietly, keeping company with a galaxy shaped long before they arrived. Andromeda holds the title of the nearest large spiral to our own. It rivals the Milky Way in size, and in some measurements exceeds it. On dark, clear nights, its light reaches Earth after crossing an almost unthinkable stretch of space. Andromeda is not just a neighbor. It is a mirror, showing roughly what our own galaxy might look like from far outside it. Light leaving Andromeda tonight departed more than 2 million years ago. It has crossed that distance steadily, at the same unchanging speed, arriving only now at your eyes. Whatever shape Andromeda holds at this very moment remains unknown to us, hidden somewhere ahead in time. What we see is simply a very old letter, finally delivered. Its journey outlasted every human who has ever lived. Simon Marius recorded Andromeda through a telescope in the early 1600s, one of the first to note its faint cloud-like glow. He described it as a candle seen through horn, dim and diffuse, without knowing it was an entire galaxy. Centuries would pass before its true nature was understood. His careful notes, made in a quiet study, marked one of the earliest formal glimpses of another galaxy entirely. Seen with the naked eye, Andromeda appears as little more than a faint, elongated smudge low in the sky, yet its true span stretches across several widths of the full moon, far larger than most people assume. Only its distance shrinks it down to something so easily overlooked. What looks like a whisper of light is, in truth, an enormous galaxy hiding in plain sight. Beside Andromeda sits Triangulum, a smaller and quieter spiral galaxy. Its arms wind loosely, its light dimmer, its presence easy to miss beside its brighter neighbor. Triangulum lacks Andromeda's grand bulge, giving it a more modest, open structure. Even so, it holds its own slow turning of stars and gas, spinning patiently in the same corner of space. Several spiral galaxies belong to a loose gathering called the local group, bound together by mutual gravity, rather than any rigid structure. The Milky Way and Andromeda dominate it, but smaller members drift nearby as well. None of these galaxies race apart the way most galaxies do across the wider universe. Instead, they linger together, held in a slow, patient orbit around one another. Andromeda and the Milky Way drift toward one another, closing the distance between them by degrees. Their motion is imperceptibly slow to any single lifetime, yet steady across the ages. Neither galaxy notices the approach. There is no signal, no urgency in the pull. Two enormous structures simply continue moving the way gravity has always shaped their paths. Edwin Hubble measured the distance to Andromeda and settled an argument that had lingered for years among astronomers. Before his measurement, many believed spiral nebulae were simply clouds inside our own galaxy. Hubble's careful observations placed Andromeda far beyond the Milky Way's edge, proving it to be an entire galaxy in its own right. His quiet calculation reshaped how everyone since has understood the universe's true scale. Astronomers once argued whether spiral nebulae belonged inside the Milky Way or drifted far beyond it. For decades before Hubble's measurement, the question had no settled answer. Some viewed these hazy patches as nearby clouds of gas, still forming within our own galaxy. Others suspected they were entire galaxies, scattered across a far larger universe. The debate lingered in observatories and academic journals alike, unresolved by any single observation. Somewhere beyond the window, a low hum rises and fades, arriving and receding like breath. It could be wind moving through the eaves, or simply the house settling into night. Let it pass without needing a name. Your body can loosen the same way that sound does, rising, drifting, and letting go. Shoulders sink lower into the mattress. Each breath grows longer than the last, unhooked from the shape of the day. Henrietta Leavitt spent her days at the Harvard College Observatory, measuring the brightness of stars on glass photographic plates. Among thousands of dim points of light, she noticed something patterned in stars that flickered on and off. Their brightening and dimming followed no random path, it repeated, steady as a heartbeat. That pattern, tucked inside stacks of plates, would later unlock distances no one else had managed to measure. Cepheid variable stars swell and shrink over days or weeks, brightening and dimming in a steady cycle. That cycle isn't random. It ties directly to how much light the star actually produces. A cepheid that pulses slower is intrinsically brighter than one that pulses fast. By timing the rhythm, astronomers can work out a star's true luminosity, even from unimaginable distances away. That timed pulse became a cosmic ruler, reaching farther than anything measured before it. Once astronomers matched a cepheid's period to its brightness, they could calculate how far its light had traveled to reach a telescope. Suddenly, distances to nearby star clusters could be compared against distances stretching across whole galaxies. Nebulae that once seemed unreachable came within calculation for the first time. High in the constellation Canes Venatici hangs the Whirlpool Galaxy, its two arms curved in a wide, graceful spiral. Nearby drifts a smaller companion galaxy, caught in a long gravitational embrace with its larger neighbor. Their mutual pull has stretched and sharpened the Whirlpool's arms into striking, well-defined lanes of stars. The pairing has lasted for hundreds of millions of years, neither galaxy pulling free. Charles Messier first logged the Whirlpool as a dim, fuzzy patch while hunting for comets across the night sky. He had no way of knowing it was an entire galaxy, its light gathered from countless stars far beyond our own. To him, it was simply an object to note and move past, catalogued among dozens of similar smudges. Only centuries later would its true scale become clear. Seen nearly edge-on, the Sombrero Galaxy wears a wide, dark band of dust wrapped around its bright disk. That band gives the galaxy its name, resembling the brim of a wide hat tilted against starlight. Inside, an unusually large, luminous bulge glows at its center, packed with countless older stars. Its edge-on angle happens to be little more than a chance of orientation. Spreading its arms in a loose, open pattern, the Pinwheel Galaxy scatters bright knots of star formation across its disk. Its structure looks less tightly wound than the Whirlpool's, arms fraying gently at their edges rather than staying sharp. Vast clouds of glowing gas mark, where new stars are actively forming within those arms. Astronomers have counted enormous numbers of star-forming regions, scattered throughout its reach. Grand design spirals stretch two clean, sweeping arms nearly the full way around their disks, unbroken and easy to trace. These arms stand out sharply against the darker gaps between them, giving the galaxy a symmetrical, almost deliberate appearance. The Whirlpool itself is often used as the clearest example of this shape. Such well-defined structure likely depends on steady gravitational influence, whether from a companion galaxy or the galaxy's own internal dynamics. Not every spiral wears such tidy arms. Flocculent spirals show patchy, broken segments, arms that fray and scatter rather than sweep cleanly around the disk. No single dominant curve organizes their light. Instead, dozens of short, feathery strands drift across the galaxy like wisps of smoke caught midair. Each patch still marks fresh star birth, only scattered rather than aligned. Grand design arms may owe their clean sweep to something invisible, a density wave. This is a pattern moving through the disk, not a fixed structure of stars. Astronomers now suspect it acts like a slow-moving wave of gravity, shaping stars into an orderly line, even as the stars themselves keep moving. The wave persists longer than any single star's path through it. It may explain why some spirals look so sharply drawn, while others stay loose. Let warmth begin somewhere small tonight, perhaps in the center of your chest. Let it spread outward from there, the way light spreads from a low flame in a dark room. Feel it reach your arms, loosening them against the bed. Let it move into your hands, your fingers, until they rest without effort. Let it settle into your legs, your feet, until your whole body feels warmed through, heavy and held. Picture a field of wheat under a passing wind. The wind itself moves forward, but each stalk only bends and returns, staying where it grew. A density wave crosses a galaxy's disk in much the same way. The wave travels ahead, gathering stars and gas briefly as it goes. What moves is the pattern, not the material itself. Stars entering the wave slow for a while, crowding closer together than usual. Gas clouds do the same, compressing as they pass through. Neither stays trapped. Each continues on its own orbit once the wave has moved ahead. Only the momentary crowding remains behind, visible as a brighter lane. The wave keeps moving, and new stars keep entering it in turn. That momentary crowding is what makes a spiral arm glow. Gas compressed by the passing wave collapses more easily into new stars. Those young stars burn bright and blue, lighting the arm before they drift beyond it. The arm itself never runs out of material because fresh gas keeps arriving as the wave keeps circling. What we see as a lit spiral arm is really a place where creation is caught in the act. Bertil Lindblad, working in the 1920s, proposed that a spiral arm might not be a fixed river of stars at all. He suggested instead that it was a pattern, sustained by gravity, through which stars simply passed. His idea ran against the intuition that arms were solid, physical structures holding their stars in place. It took decades of further work before the wave picture he described became widely accepted. His name is now tied permanently to the mathematics describing how such waves move. Arms do not always need an internal wave to appear. A small companion galaxy passing near a larger disk can tug on it with its own gravity, however gently. That tug can stir the disk stars and gas into a spiral response, much like a pebble dropped into still water sends rings outward. The companion need not collide or even come especially close. Its passing influence alone can be enough to leave a lasting mark. A closer encounter leaves a more dramatic signature. When two galaxies pass near enough for their gravity to pull strongly on one another, the larger disk can respond by growing two long, sweeping arms almost overnight by galactic standards. What had been an unremarkable, evenly spread disk becomes something newly patterned, its material drawn outward in curving streams. The encounter itself may last only a few 100 million years, yet the arms it leaves behind can persist long after the two galaxies have drawn apart again. Barred spirals hold a straight lane of stars running through their very center, and that bar does more than shape the galaxy's look. It acts like a funnel, guiding gas inward along its length toward the core. Orbits within the bar are arranged so that gas loses a little energy with each pass, sinking closer to the center over time. This slow inward drift can continue for a very long stretch of the galaxy's life. What begins scattered across the disk eventually gathers near the galactic heart. Gas that sinks along a galaxy's bar does not always stop at the core. Some of it continues inward, drawn toward the supermassive black hole waiting at the center. This feeding happens gradually, a trickle rather than a flood, spread across many millions of years. The black hole grows almost imperceptibly, meal by distant meal. Nothing about the process, looks dramatic from the outside. Every part of a spiral galaxy's disk does not travel at the same pace. Stars nearer the center complete their orbits far more quickly than those farther out, a pattern astronomers call differential rotation. A star near the core might circle many times in the span it takes an outer star to circle once. This uneven motion stretches and shears the disk continuously. It never rotates as a single rigid wheel. Such uneven motion would seem to wind spiral arms into tight knots within a few rotations. Yet observed galaxies show arms that remain recognizable for hundreds of millions of years. The pattern itself moves independently of the stars threading through it, which is why it survives the disk's shearing. Stars come and go, but the shape lingers. This puzzle guided much of the 20th century's thinking about how arms actually work. Let your attention settle now on something small and slow, like the last curl of smoke rising from a candle just blown out. It bends, thins, and loses itself into the dark air above it, in no hurry to be anywhere. Your breath can move the same way, rising and dissolving without effort. There is no shape it needs to hold. Let your body follow that same soft unraveling, loosening a little more with each breath until thought itself thins like smoke and fades from view. Fine grains of dust drift through every spiral arm, scattered among the stars and gas. Starlight passing through this dust loses some of its blue light first, arriving redder than it left. Thick enough patches can block visible light almost entirely, hiding whole regions behind a dark curtain. This is part of why a galaxy's center often looks dim from certain angles. The dust itself is made largely of carbon and silicate grains, born in the winds of older stars. Hidden within those same dusty arms lie molecular clouds, vast and cold, where hydrogen gathers into pockets dense enough to collapse. Inside such a cloud, gravity slowly pulls scattered gas into knots that will eventually ignite as stars. The process takes place entirely in darkness, invisible to ordinary light. It can unfold across millions of years before a single star ever shines. What looks like empty space between stars is often exactly where new ones are forming. One of these giant molecular clouds can hold more mass than 1 million suns combined, spread across dozens of light years. Such a cloud looks from a distance like little more than a smudge of shadow against the starfield. Within it, though, lies the raw material for entire clusters of future stars. Its gravity is barely strong enough to hold itself together, poised on the edge of collapse. Given enough time, gravity usually wins. Stars born together inside such a cloud often stay loosely bound afterward, forming what astronomers call an open cluster. These groupings drift within a spiral arm for a while, their members sharing a common birthplace and a common age. Over a few 100 million years, the gentle pull of the wider galaxy tugs them apart. Each star eventually goes its own way, scattered along its own path around the galactic center. The cluster's identity fades, though its stars continue on. Among the stars born in these arms, the most massive burn through their fuel astonishingly fast. A star many times heavier than the Sun might shine brilliantly for only a few million years before its life ends. By stellar standards, this counts as a brief flash rather than a long career. Lighter stars, by comparison, can shine for billions of years. Mass, more than anything else, decides how quickly a star's story closes. When one of these massive stars finally exhausts itself, it ends in a supernova, briefly outshining its entire home cluster. The shock wave from that explosion presses outward into the surrounding gas, compressing nearby clouds. Sometimes, that compression is enough to trigger new star formation close by. In this way, one generation's ending can quietly seed the next one's beginning. Spiral arms carry on lighting themselves this way, star by star, across long stretches of time. Within a spiral galaxy's disk, two populations of stars occupy different heights above the midplane. A thin layer holds young, blue stars still close to the spiral arms that made them. A slightly thicker layer surrounds it, filled with older stars. Their orbits wander farther out. Both layers share one galaxy, quietly stacked together. These two disks preserve two separate chapters of a galaxy's history. The thin disk records recent, orderly star formation. The thick disk remembers something rougher. Its stars often formed before the galaxy fully settled into its current shape. Reading both layers together lets astronomers piece together a timeline no single snapshot could reveal. Far from a spiral's bright core, the disk does not end abruptly. Instead, its light thins gradually into a faint stellar halo. Stars there sit sparse and dim, scattered far beyond the visible arms. Few instruments catch them at all. The transition feels less like an edge than a fading whisper. Some spiral disks tilt upward at their outer edges, like the brim of a hat lifted at both edges. Astronomers call this shape a warp. It appears in a good fraction of nearby spirals, including our own. The cause often traces back to gravity from a passing companion galaxy. Even a broad, settled disk can bend under a distant pull. Let the muscles around your jaw loosen now, just slightly, the way a hand unclenches when it finally has nothing to grip. Your eyelids have grown heavy, resting rather than holding. Behind them, the dark is wide and unmeasured, a space with no edges to trace. You don't need to see anything there. You can simply let it be dark, and let the dark hold you, breath by slow breath. Gravitational tides from neighboring galaxies can bend a spiral disk over long stretches of time. A close pass, even without a collision, tugs unevenly at different parts of the disk. Outer stars, farther from the galaxy's own pull, feel it most strongly. The change unfolds across ages. The disk lifts at its edges, echoing the warp described a moment ago. Magnetic fields trace spiral patterns of their own, aligned loosely with the arms of stars and gas. These fields stretch across thousands of light-years, far too faint to feel. Radio telescopes reveal their shape by the way they twist starlight passing through dust. A galaxy, it turns out, holds an invisible architecture of its own lines. Cosmic rays travel along these magnetic field lines, threading through a galaxy's disk. These are particles, mostly protons, flung outward by exploding stars and other violent events. They rarely travel straight. Following the curving magnetic paths instead, their journeys can stretch for millions of years before they escape or scatter. Even empty-looking space carries this quiet traffic of unseen particles. Spiral galaxies typically contain a few 100 billion stars within their bright disks. That number is hard to hold in mind, let alone count star by star. No single star stands apart. Each one differs slightly in mass, color, and age. Together they form a slow, glowing crowd, wheeling around a shared center. Not every star in a spiral galaxy shares the same age. Some formed only a few million years ago, still bright and blue within the arms. Others have burned quietly for billions of years, born long before the galaxy took its current shape. The disk, seen as a whole, is a patchwork of many separate beginnings. No single moment created it. Countless small ones did. Edwin Hubble sorted galaxies into a simple sequence of shapes that still guides astronomers today. In the 1920s, he arranged thousands of photographic plates into a branching diagram, moving from smooth ellipticals toward looser spirals. He gave the diagram a name that stuck, the tuning fork. Astronomers still sketch it on whiteboards, nearly a century later. It remains one of the simplest tools for describing something so vast. His scheme placed spirals along a fork, tightly wound on one branch and loosely wound on the other. Early types wound their arms close around a bright, tight core. Late types spread their arms wider, looser, sometimes barely holding together. Hubble labeled these differences with simple letters, nothing more. The letters said little about a galaxy's age. They only described its shape, as seen from far away. Gerard de Vaucouleurs later expanded that scheme to capture bars, rings, and finer details of shape. Working through the 1950s and 60s, he added new symbols for features Hubble's fork had left out. A bar through the center earned its own mark. A ring around the arms earned another. His revised system grew more detailed, almost like a second language for describing galaxies. Modern surveys still borrow this old vocabulary of arms, bars, and rings to describe spiral galaxies. Astronomers cataloging thousands of galaxies each year still reach for these decades-old terms. New instruments capture detail Hubble and de Vaucouleurs never imagined. Yet the underlying words remain useful, simple enough to describe a shape at a glance. Old language, it turns out, can still hold up under new light. A galaxy's shape alone hints at its history, though it rarely tells the whole story. Tightly wound arms might suggest a calm, undisturbed past. Loose, patchy arms might hint at a recent disturbance. But shape alone cannot reveal a galaxy's age, its gas content, or the mergers it may have survived. Appearance offers a starting clue, not a full account. Feel the breath moving in and out on its own, low in the chest. Notice how each exhale seems to last a beat longer than the one before it. There's nothing to adjust, nothing to time. The air simply continues, rising and falling like a slow tide against a shore that never needs to be told to wait. Let your next breath arrive whenever it wants to come. Certain spiral galaxies wear an inner ring, circling just outside their bar. This ring forms where gas, funneled inward by the bar, piles up and slows into a stable path. Stars can form along this ring, tracing a bright circle around the galaxy's core. Not every barred spiral shows one. When it appears, it marks a quiet balance between the bar's pull and the gas orbiting around it. Outer rings occasionally encircle a spiral galaxy's arms altogether, formed long ago by some gravitational disturbance. A close pass from a neighboring galaxy can pull material outward, looping it into a faint ring beyond the main disk. These outer rings glow faintly, made of stars and gas stretched thin. They mark the memory of an old encounter, one that reshaped the galaxy's outer reaches without destroying its spiral form. Polar ring galaxies show a ring of stars and gas orbiting almost perpendicular to the main disk. Seen from the right angle, they look like two galaxies crossed at right angles. The ring circles above and below the central disk, rather than around its edge. Fewer than a few hundred such galaxies are known. Their odd geometry makes them among the most visually striking objects in the deep sky. Such rings likely formed when a smaller galaxy's material was captured and torn into a new orbit. Gravity stretched the smaller galaxy's gas and stars into a long stream, which eventually wrapped itself around the larger galaxy's poles. Over time, that stream settled into a stable ring, orbiting on its own tilted path. The encounter that created it may have finished billions of years ago, though the ring itself endures. Ring galaxies of this kind remain rare among the broader population of spirals. Most disks keep their familiar shape, arms winding outward without any surrounding loop. Rings like these are uncommon. A ring requires a particular kind of encounter, a specific angle, a certain timing. Astronomers have catalogued only a modest number across the observable sky, each one breaking from the pattern spirals usually follow. Lenticular galaxies sit between spirals and ellipticals, holding a disk but no visible arms. They keep the flattened shape of a spiral, spinning stars around a central bulge. No spiral pattern lights it. Dust lanes are sparse or absent entirely. Astronomers place them in their own category. Neither fully wound nor fully smooth, a shape caught midway between two familiar forms. Long ago, a lenticular galaxy may have spun with spiral arms of its own. Gas is what lights an arm, and once that gas is spent, the arms have nothing left to trace. Star formation slows, then stops. What remains is a disk of older stars, still turning, but no longer patterned into visible spirals. The shape softens with time, smoothing itself the way a current dies once its source runs dry. Steady gas supply keeps a spiral's arms lit with fresh, young stars. Without new material, star birth has nothing to work with. The cycle never truly stops. Hydrogen clouds must gather, cool, and collapse again and again across a galaxy's disk. This depends on a continuous flow, not a single reservoir spent once and forgotten. A spiral, in a sense, must keep feeding itself to keep glowing. Gas eventually runs low, and a spiral's arms fade into a smoother, dimmer disk. Star formation slows first at the outer edges, where material has always been thin. The glow grows dimmer. Bright blue stars that once traced the arms burn out and are not replaced. What remains settles into an even glow of older, redder light, the shape intact, even as its brightest signature slips away. Intergalactic space holds cool gas that occasionally streams into a spiral's disk. This accretion can replenish fuel that would otherwise run out. Nothing arrives quickly. The process unfolds across enormous stretches of time, drop by drop, rather than in any sudden rush. A galaxy in a rich environment may keep forming stars far longer than one left isolated. Its supply, in effect, is borrowed from the space around it. For a few moments now, let the weight of the day settle into the mattress beneath you. Start with your feet, letting them grow heavy, then your calves, then your knees. Let that heaviness rise, moving upward through the hips, the lower back, each part sinking a little deeper. Your arms follow, heavy at the shoulders, heavy at the wrists, just the bed holding you. Filaments of cool gas stretch between galaxies, threads spanning distances too vast to picture easily. These strands feed disks from the space between them, carrying material into galaxies still hungry for fuel. The web is vast. Telescopes have traced these filaments in dim outline, mapping the skeleton of matter connecting one galaxy to the next. A spiral supply is never truly isolated, drawing from something far larger than itself. Quieter neighborhoods, away from the crowded hearts of galaxy clusters, tend to host more spiral galaxies. In these looser surroundings, encounters are gentler and less frequent. Space here is open. A disk has more room to keep its shape without being stripped or disturbed. Spirals seem to thrive where gravity's pull comes from fewer directions at once, a kind of preference for elbow room. Elliptical galaxies dominate dense clusters, while spirals favor looser groups and open space. Where galaxies crowd together, collisions and stripping reshape disks into rounder forms. This pattern held. Where space is thin, spirals persist, undisturbed for far longer. Environment, it turns out, shapes destiny nearly as much as any single galaxy's own history. Ram pressure builds when a spiral galaxy plunges through the hot, thin gas that fills a cluster's core. That gas acts almost like a headwind, pressing against the galaxy's own reserves of hydrogen. Motion alone can do this. Over time, the pressure peels gas away from the disk, leaving stars behind but stripping the fuel meant to make new ones. The galaxy keeps its shape, briefly, but not its supply. Stripped of gas, a spiral can lose its arms entirely, the bright lanes fading into a smooth, starved disk. Without fresh clouds collapsing into stars, the blue light that once traced each arm dims. What remains looks older than it is. Astronomers sometimes find these pale disks drifting through clusters, spiral in form but hollow in function, a shape without its former light. Spiral galaxies range enormously in size, from modest dwarfs barely a tenth the width of the Milky Way to sprawling giants many times larger. Between these extremes lies most of what fills the night sky. Size varies. Some spirals hold just a few billion stars, others several hundred billion, each shaped by its own long history of growth and gas. Among the largest known spirals, some stretch several times the width of the Milky Way's own disk. Their arms extend far beyond what our galaxy's structure would suggest is typical. Such galaxies are rare. They tend to sit in unusually gas-rich surroundings, drawing in material for eons, building outward slowly rather than inward toward a busy core. Malin 1 is a giant spiral discovered almost by chance, hidden within the results of a routine survey of galaxy distances. It sat in the data for a while before anyone noticed how strange it truly was. Its disk was unusually broad and unusually dim. Astronomer David Malin, reviewing an old photographic plate in the 1980s, recognized what earlier glances had missed entirely. Its disk proved so dim that earlier surveys had simply passed over it, mistaking the faint smudge for background noise or an artifact of the film. Brightness alone had guided most searches before then. A galaxy this large, spread this thin across space, gave off so little light per area that ordinary scans overlooked it, hidden by its own sheer size. Astronomers noticed Malin 1's true extent only when they let an exposure run longer than originally planned, coaxing faint light out of the dark. The extra minutes revealed spiral arms stretching far past what anyone expected. Nobody had aimed for this. A longer look, held a little past the usual limit, uncovered one of the largest known spiral disks in the observable universe. Somewhere far off, a sound rises without asking to be noticed, wind moving low across a rooftop or a pipe settling somewhere deep in the walls. It swells for a moment, then thins back into silence. There is no need to trace where it came from. Let it pass through the room, the way it wants to, arriving, fading, leaving the air a little stiller than before. Your breathing can follow that same slow rhythm now, rising, falling, asking nothing of you. Dwarf spirals exist too, smaller cousins of the giants, spinning quietly through less crowded corners of space. Their arms are thinner, their star fields sparser, their light softer against the dark. Few notice them, yet even at reduced scale, they hold the same graceful architecture, the same slow turning, the same patient balance between gravity and motion. A galaxy's spiral shape can persist even when its total mass is modest, proof that grandeur has never been a requirement for structure. Smaller disks manage the same trick as giants, gathering gas into arms, spinning stars into place. Mass helps, but it isn't everything. Shape seems to follow from balance, not size alone, a pattern gravity is willing to build at almost any scale. Bulges at a spiral center vary widely in shape and size. Some are small, delicate cores, barely swelling above the disk. Others rise broad and round, dense with old reddish stars. A bulge like this can hold billions of stars that formed long before the surrounding disk finished taking shape. Its size often marks how eventful a galaxy's youth once was. Bigger bulges often, though not always, correlate with a more massive black hole at a galaxy's core. Astronomers have measured this pattern across many nearby spirals, finding heavier bulges paired with heavier hidden anchors. The link is not exact. Some galaxies break the pattern, carrying oversized bulges with modest black holes, or the reverse. Even so, the general trend has held steady across countless surveys. This relationship between a bulge and its black hole suggests the two grew together, shaped by shared history rather than by coincidence. Gas falling toward a galaxy's center may have fed both the growing black hole and the surrounding swell of stars at once. Growth in one seems tied to growth in the other. It hints at a long, intertwined process reaching back to a galaxy's earliest years. No one yet knows the full mechanism by which a galaxy and its black hole seem to grow in step. Feedback from the black hole may regulate star formation nearby, or shared gas reservoirs may simply feed both at similar rates. Theoretical models offer several competing explanations. None fully accounts for every galaxy observed. The question remains open, patiently, at the edge of current understanding. Spiral galaxies were once thought to be static wheels, fixed in shape for all time. Early observers imagined their arms as solid structures, carried around like spokes on a cart. That image felt natural, given how orderly the arms appeared in photographs. It would take decades of careful mathematics to reveal something stranger moving beneath that stillness. That view changed once astronomers modeled how gravity lets a disk pattern move independently of its stars. Calculations showed that an arm could behave like a wave, a shape drifting through the disk while individual stars passed through it. The stars themselves were not glued to the arm at all. This realization quietly rewrote how galaxies were understood to hold their form. Computer simulations in the latter 20th century first showed spiral arms forming and dissolving naturally. Researchers fed simple physical rules into early machines and watched galaxies take shape on glowing screens. Arms curled outward, brightened, and faded, all from gravity alone. No one had to force the pattern by hand. The simulations simply let physics run, and spirals appeared on their own. Those simulations suggested that spiral arms can be transient, reforming again and again over a galaxy's life. An arm might brighten, stretch, and dissolve, only for another to gather itself elsewhere in the disk. The galaxy as a whole keeps a spiral look. Its particular arms are never quite the same twice. Structure persists even as its details keep shifting. Let warmth begin now in your hands, resting wherever they happen to lie. Feel it pool first in the palms, faint and low, then spread up through the wrists. It moves the way heat moves, through a stone left in sunlight, unhurried, without effort. Let that warmth climb the forearms next, loosening whatever tightness gathered there through the day. There is only this slow rising heat, and the stillness it leaves behind. A single spiral arm might last a few 100 million years before fading, with another arm taking its place elsewhere in the disk. That span sounds immense, yet it is brief against a galaxy's full lifetime. Arms come and go like slow tides across the disk's surface. Each one lights up with young stars, ages, and dims. The galaxy's overall spiral shape simply outlives any single arm within it. Across billions of years, a spiral's arms can flicker like light patterns dancing on moving water. A ripple brightens, drifts, and dims into the surface again. No single ripple lasts, yet the play of light never stops. Seen from far enough away, a galaxy's arms behave the same way, always shifting, always somehow still recognizable as the same shining shape. Spiral galaxies were more common in the earlier universe than astronomers once expected. Early telescope surveys assumed young galaxies would look chaotic, clumped, and disordered. Instead, orderly disks kept turning up in surprising numbers. Structure, it seemed, could arrive early. That finding quietly reshaped how astronomers pictured the universe's youth. Deep space telescopes have found orderly spiral shapes appearing earlier than astronomers once predicted. Peering across billions of light years means peering back across billions of years of time. What those telescopes found, again and again, were disks already turning, already tracing arms. the universe seemed to favor order sooner than expected. James Webb Space Telescope located well-formed spirals reaching back more than 10 billion years. That is older than most stars in our own galaxy's disk. The light from these distant disks left home when the universe was still young. Somehow, gravity had already arranged their gas and stars into graceful curves. Such early spirals suggest galaxies can organize themselves into disks surprisingly quickly. Given enough gas and enough time, gravity seems to favor rotation over chaos. Matter settles, flattens, and begins to turn. The process may take far less time than once assumed. Order, in this sense, appears to be nature's default. Cosmologists still debate exactly how such young spirals settled into such ordered shapes so quickly. Gravity alone may explain part of it. Turbulence in early gas clouds may explain another part. No single model yet accounts for every early spiral observed. The question remains open, studied galaxy by galaxy, disk by disk. Settling into a lasting spiral shape likely requires a long, undisturbed stretch of growth. Gas needs time to cool, gather, and spread into a flattened disk. Stars need time to form in an orderly rhythm. Disruption at the wrong moment can undo all of it. Patience on a cosmic scale appears to matter. Mergers and collisions, common in the crowded early universe, can disrupt a disk before it fully settles. Two galaxies meeting head-on can scramble gas and stars alike. Arms that were just beginning to form may unravel entirely. Early galaxies lived in a rougher neighborhood than the quieter universe of today. A galaxy that avoids major collisions has a better chance of keeping a lasting spiral shape. Quiet surroundings allow a disk to settle without interruption. Fewer disturbances mean fewer chances for arms to unravel. Some early galaxies simply happen to grow up in calmer corners of space. Their patience left them with arms that endured. Let your eyelids grow heavy now, the way an ember slowly loses its glow. No sudden dimming, only a soft fading, moment by moment, until the light settles into darkness. Let your breathing follow that same fading rhythm, slower, lower, dimmer with each breath. There is only this gradual settling, this small ember cooling toward rest, and the stillness that follows it. Long ago, the Milky Way grew larger by absorbing smaller galaxies nearby. Their stars didn't vanish. Instead, they were woven into the outer halo, scattered into loose orbits above and below the disk. Some of those stars still drift far from where they began, carrying traces of a history that wasn't originally its own. The Milky Way, in this sense, is partly a mosaic of older galaxies swallowed over time. Traces of an old collision still linger in the orbits of stars near the Sun. Astronomers named it the sausage merger, after the elongated shape its stars trace across velocity maps of the sky. These stars move on paths unlike their neighbors, stretched and looping in ways only visible through motion, not appearance. Their orbits remember an event no living eye witnessed. That merger occurred roughly 8 to 11 billion years ago, when a smaller galaxy fell into the young Milky Way. The impact stirred the disk, lifting stars into wider, thicker orbits than before. Astronomers think this event helped build what is now called the thick disk, a layer of older stars sitting above and below the thinner, younger one. The scars of that fall remain written into stellar motion today. Despite that past upheaval, the Milky Way's spiral pattern endured and rebuilt itself. The disk didn't stay disturbed forever. Gas settled again, stars found new order, and the arms reappeared much as they had before. Gravity, given enough time, seems to restore the pattern it briefly lost. Order returned, unremarkable, the way it usually does. Spiral arms seem resilient, able to reform even after a galaxy is jostled by a smaller merger. Gravity keeps threading gas and stars into fresh density waves. A shaken disk isn't broken beyond recovery. Given time, it tends to fall back into a familiar swirl. Resilience in a galaxy looks like time given enough room to work. A larger collision, however, can unravel a spiral's shape entirely, where a small merger only stirs the disk. A major one can tear it apart. Arms lose their footing, gas scatters, and the tidy pinwheel dissolves into something rougher. Not every disturbance heals the same way. Scale decides whether a spiral survives its history intact. Two colliding spiral galaxies can pull long tidal tails of stars and gas out into space. Gravity from each galaxy tugs at the other's outer disk, stretching material into thin, curving streams. These tails can span hundreds of thousands of light years, trailing behind the merging pair like slow-moving ribbons. What was once a tidy spiral edge becomes a loose thread cast into the dark. The antennae galaxies show two spirals mid-collision, their arms stretched into glowing streamers. Named for the two long tails curving away from the wreckage like an insect's antennae, the pair drifts closer with each passing era. Inside the tangled cloud, new stars are igniting by the thousands, born from gas compressed in the collision itself. Chaos and creation here share the same moment. Such collisions unfold across hundreds of millions of years, far slower than they appear in any single image. A photograph freezes one instant of a process too long for any lifetime to witness. What looks like a sudden collision is really a long, gradual drift, measured in the same spans that shape stars and galaxies alike. Stillness in the picture hides motion too vast to see. Eventually, colliding spirals come to rest as a single, rounder galaxy with no arms left at all. The tidal tails fall back inward or drift away. Gas turns turbulent. Star formation flares, then fades as fuel runs short. What remains is a smoother, dimmer shape, its spiral structure gone for good. Two winding galaxies end their story as one still sphere. Notice the muscles around your eyes now, small and often forgotten. Something there can loosen, like a page lying flat after being held open too long. Let your eyebrows drop their weight. Let the eyelids grow heavy as warm wax. Behind closed lids, the dark widens, shapeless, asking nothing of you. Rest there a while, in that private dark. Astronomers call this common outcome an elliptical galaxy, the eventual fate of many mergers. Round and smooth, it lacks the winding arms that once defined it. Its stars now orbit in looser, more scattered paths, no longer bound to a single spinning pattern. Many of the largest galaxies in the universe carry this rounded shape. It is less an ending than a different kind of shape entirely. Andromeda and the Milky Way are drawing closer, expected to meet in a slow collision roughly 4 billion years from now. Neither galaxy will vanish suddenly. The approach continues across an immense stretch of time, closing the distance by fractions with each passing age. When the meeting finally comes, it will unfold over hundreds of millions of years, never as a single moment. Their meeting will not resemble two objects crashing so much as two mists slowly mingling. Stars sit so widely spaced that the galaxies pass through each other more like fog than solid stone. Gas clouds will compress here and there, sparking bursts of new star birth. No shattering impact will mark the moment. It will feel, from any vantage, like weather changing more than any collision happening. Distances between stars are vast enough that a direct collision remains unlikely for nearly all of them. Picture two swarms of fireflies passing through one open field, each continuing its own path undisturbed. The Sun itself will likely keep orbiting, untouched by any stellar collision. It is gravity, not contact, that will carry out the reshaping. Gravity alone will be enough to reshape both galaxies over billions of years of gradual interaction. Each galaxy's mass pulls at the other's disk, stretching spiral arms into long tidal streams. Orbits shift, stars scatter into unfamiliar paths, and the tidy structure erodes bit by bit. No explosion is needed for such change, only vast stretches of time. Astronomers expect the aftermath of this meeting to come to rest as a single elliptical galaxy, joining the shape so many mergers eventually take. Some call this future galaxy Milkomeda, a blend of both present names. It will hold the stars of both disks, its arms gone, its glow spread into a smooth, round shape. Something of both parent galaxies will endure inside it. Long after that meeting, the Milky Way's spiral shape as we know it will have dissolved into something rounder and less structured. The arms that once traced star-forming lanes will no longer exist in any recognizable form. What began as a flattened disk with sweeping arms will end as a fuller, rounder gathering of stars. This is less an ending than a long completion. Star formation across the universe has slowed since the era when spiral galaxies were more common and gas ran more abundant through their disks. The universe once burned brighter with newborn stars fueled by deep reservoirs of hydrogen. Much of that gas has since been used, locked away inside stars already formed. Fewer galaxies now hold the raw material for such vigorous birth. Many spiral galaxies will run low on the gas needed to keep their arms alight, exhausting the fuel that once lit their winding lanes. Star formation there will dim gradually, region by region, rather than all at once. Arms that once glowed with young blue stars will fade into a smoother, dimmer disk. What remains will look far quieter than any spiral seen tonight. A future universe may hold fewer bright spiral arms than the sky offers tonight. As galaxies use up their gas, fewer new stars ignite along the winding lanes that once defined them. The night sky of some distant era may glow with rounder, quieter shapes instead. Spiral galaxies, so common now, may become the rarer sight. Let the exhale grow a little longer now, without any effort to make it so. Each breath out can last a moment past where it used to end. There is no need to count them, only to notice one becoming another. Let your ribs settle a little lower with each release. The body already knows how to rest. None of this unfolds on any time scale a person could ever notice within one lifetime. A human life passes in what amounts to a flicker against a galaxy's turning. Arms brighten and fade over hundreds of millions of years, far beyond any single watch. What feels permanent in the sky is simply slow beyond our senses. Nothing about it demands to be witnessed all at once. Every spiral galaxy alive tonight is living through an ordinary chapter of a story spanning billions of years. None of them are finished. None of them are new. Each one sits somewhere between its birth and its eventual quiet ending, spinning steadily through its middle years. Ours is no exception. We happen to be watching during one page of a very long book. Radio telescopes, built originally to study distant static, ended up mapping our own galaxy's structure. Engineers first pointed dish antennas skyward to solve problems in communication, not astronomy. What they found instead reshaped how galaxies could be studied. A tool meant for practical noise became a window onto the cosmos. Sometimes discovery arrives sideways, through instruments built for something else entirely. Carl Jansky first detected a hiss of radio noise from the sky while investigating telephone interference. In the early 1930s, working for a telephone company, he built a rotating antenna to track down static disrupting transatlantic calls. Among ordinary sources of interference, one steady hiss stood apart, shifting with the stars rather than the weather. It traced back to the direction of the Milky Way's center. He had found the sky itself humming. That accidental discovery opened an entirely new way of studying spiral galaxies without visible light. Radio waves pass through dust that blocks ordinary starlight, revealing structures otherwise hidden. Astronomers soon realized they could listen to a galaxy as much as look at it. A whole layer of the universe, once silent to human eyes, became audible in its own quiet way. The sky had more to say than light alone could tell. Later radio surveys of hydrogen gas revealed spiral arms that no optical telescope could trace. Cold hydrogen, invisible in ordinary light, emits a faint radio signal that maps its location across a galaxy's disk. Following that signal, astronomers charted spiral arms reaching far beyond where starlight faded into darkness. The Milky Way's own arms, hidden behind dust from our vantage point, finally took shape on radio maps. A hidden structure became visible through an entirely different sense. Infrared telescopes later pierced the dust that hides much of a spiral galaxy's central structure. Where visible light scatters and dims among dense clouds, longer infrared wavelengths pass through more easily. Peering through that veil, astronomers glimpsed crowded star fields and the bar of stars running through many galactic cores. Regions once described only in silhouette became populated with detail. The center, long obscured, slowly came into view. Each wavelength of light reveals a different layer of a spiral galaxy's hidden architecture. Visible light shows the familiar glow of stars. Radio waves trace cold gas. Infrared uncovers dust-shrouded cores. Together, these views assemble something closer to a complete portrait than any single image could offer. A spiral galaxy, seen this way, becomes less a single picture than a layered composition. Each layer patiently adds to what came before. Combining these views lets astronomers build a fuller portrait of galaxies too vast to see whole. Visible light, radio waves, and infrared each capture a different truth about the same spiral disk. Layered together, they form something closer to a full likeness than any single image could manage. No single telescope shows everything. A spiral galaxy, seen this way, feels less like a photograph and more like a memory assembled from many senses. Spiral galaxies make up roughly 2 out of every 3 bright galaxies in the nearby universe. Wherever telescopes point toward brighter patches of sky, spirals tend to outnumber their smoother, rounder cousins. They are the ones we notice first. Their arms and their gas make them easy to admire, easy to recognize from a great distance. This abundance shaped what most people picture when they imagine a galaxy at all. Let the weight of your legs sink now into whatever is holding you. First the right leg, heavy as settled sand, then the left following after in its own time. Let that heaviness climb higher, into the hips, the low back, the space beneath your ribs. Let your arms grow heavy too, resting wherever they landed. Feel the mattress take all of it, without asking anything back. Despite their abundance nearby, spirals are outnumbered by smaller, fainter dwarf galaxies overall. Across the wider universe, dwarf galaxies crowd nearly every corner of space, vastly more numerous than their grand spiral neighbors. Most hold only a few billion stars, scattered loosely, without any organized arms. They rarely draw attention in a photograph, yet together, these modest galaxies outnumber every bright spiral many times over. Most galaxies in the universe are actually far smaller and fainter than the great spirals people picture. A typical galaxy holds only a fraction of the stars found in the Milky Way, without any spiral structure at all. Grand design spirals, with their sweeping arms, are almost the exception rather than the rule. The universe favors the modest over the magnificent. Even so, it is the bright ones that shape how most people imagine a galaxy. Spiral galaxies nonetheless account for much of the light that reaches Earth from beyond our own galaxy. Their young stars burn bright, and their star-forming regions glow with an intensity dwarf galaxies rarely match. A single spiral can outshine hundreds of smaller galaxies combined. What fills a dark sky with visible glow often traces back to spirals rather than their more numerous but fainter neighbors. Brightness, it turns out, is not the same as abundance. Light from a distant spiral galaxy can travel for tens of millions of years before reaching any eye. It leaves the outer edge of one arm and crosses emptiness far larger than the galaxy itself. It never slows down. By the time that light arrives, the galaxy it left may have shifted its shape entirely. What we see was always already history. Some of the spiral light gathered by telescopes tonight departed its galaxy before Earth's oceans held any life at all. That light set out across the dark long before the first cell divided in any tide pool. It carried no memory of Earth, no knowledge that anyone would ever wait for it. Across all that distance, it simply continued, undisturbed, until a mirror finally caught it. Few messages traveled that far or that long. Every photograph of a spiral galaxy is really a photograph of its past, not its present. The image freezes light that began its journey ages before the shutter opened. Arms may have shifted, stars may have died, and the galaxy may look nothing like its portrait by now. Yet the picture remains true to the moment the light departed. A photograph, in this sense, is less a snapshot than a letter arriving very late. No observer will ever directly see a spiral galaxy's true present moment. Whatever unfolds there right now stays hidden, sealed behind the years. Its light still needs to travel. Every galaxy studied is, in that sense, a message from an earlier self. The present belongs only to the galaxy itself, never fully to the ones watching from afar. Distance guarantees this, for every star and every eye alike. Spiral galaxies continue turning throughout all of this, unaware of any observer at all. Their arms brighten with new stars and dim again, indifferent to whoever might be watching from some small blue planet. No audience is required for a galaxy to keep spinning. It simply persists, wheeling through the dark on a schedule that owes nothing to human attention. The turning itself needs no witness to remain real. Word galaxy itself comes from an old Greek term for milk, describing the pale band stretching across the night sky. Ancient viewers called it something like a milky circle, a name that outlived the language that coined it. That pale smear overhead became the root word for every galaxy ever named since. Milk and stars, joined by a single old syllable. The name endures long after its origin was forgotten. Cultures across the ancient world looked up at that same pale band and wove their own stories around it. Some called it a river of stars, others a path for souls, others a seam of spilled milk. Each version was a way of making sense of something too vast to hold in ordinary words. The band itself never changed. Only the stories draped across it shifted from people to people, generation to generation. Somewhere outside, a low sound rises and settles again, the way distant traffic thins after midnight. It comes and goes without asking anything of you. Let your shoulders answer it anyway, dropping a little further each time the sound recedes. Your breath can follow the same pattern, rising softly, falling long. There is no need to track where the sound goes when it fades. It only needs somewhere to return to, and here is enough. Only telescopes eventually revealed that pale band was made of countless individual, unresolved stars. To the naked eye, it looked like smoke or mist, a single soft glow with no seams. Early telescopes broke that glow apart, star by star, until the smoothness dissolved into multitude. What had looked like one thing turned out to be an uncountable many. The sky had been hiding its true texture in plain sight. William Parsons built a large telescope in Ireland and became one of the first to sketch a spiral shape in the sky. Working through cold nights at his family estate, he trained the instrument on a faint smudge others had barely bothered to examine. What emerged under his careful eye was a curling, armed structure, unlike anything drawn before. Nobody had proven such a shape existed until his pencil confirmed it. His drawings of a spiral nebula, made by eye alone, later proved remarkably close to photographs taken decades afterward. The curling arms he traced by hand matched the true shape captured later by cameras far more precise than any eye. Careful observation, it turned out, could outperform expectation. What one patient astronomer saw through cold glass endured as fact long after his instruments were replaced. Photography eventually replaced hand-drawn sketches, capturing detail no eye alone could hold steady long enough to see. A photographic plate could gather faint light over hours, storing what a tired observer's memory never could. Details invisible to direct sight slowly emerged from exposure. The camera did not tire, did not blink, did not forget a curve halfway through the night. It simply waited, and the galaxy revealed itself in return. Digital sensors now capture spiral galaxies in a single exposure that once required nights of patient tracking. What used to demand hours of careful guiding can now be gathered in moments, pixel by pixel, with far greater sensitivity than any plate. The galaxies themselves have not changed. Only the speed and clarity of seeing them has grown, layer by layer, decade by decade. Each new generation of instrument has revealed another quiet layer of structure within these turning disks. Eyes gave way to lenses, lenses to photographic plates, plates to digital sensors, each step uncovering finer threads of dust, gas, and starlight. No single tool has ever shown the whole picture at once. Understanding a spiral galaxy has always been a slow accumulation, one careful glance passed forward to the next. After centuries of looking, the study of spiral galaxies remains an unfinished portrait. Every generation adds a stroke that the last one could not see. New instruments reveal finer threads, and older assumptions dissolve into better questions. Nothing here has ever been fully finished, and perhaps nothing ever will be. The portrait simply grows, one careful observation at a time. Every spiral galaxy, our own included, keeps turning through a night with no true end. There is no dawn waiting at the far side of its rotation, no morning to arrive and interrupt it. It simply continues, one long orbit folding into the next, star by star, for as long as gravity holds it together. The turning itself is the only constant it has ever known. The same gravity that shapes a spiral arm also shapes the pull between two people watching the same sky. It is the same force, indifferent to scale, holding stars together and holding a hand still in the dark. Whatever draws dust into a galaxy's curve also draws attention toward another person nearby. Nothing about that pull needs to be understood to be felt. Wherever someone rests tonight, some spiral galaxy turns overhead, indifferent and vast and utterly unhurried. It does not know it is being watched, and it does not need to. It simply continues, as it has for billions of years, and will continue long after this night has passed. Let its turning be the last thought before sleep. Good night.